Hey everyone, thanks for coming. It's my pleasure to introduce Peter Lincoln from UNC Chapel Hill, where he's worked with Henry Fuchs on designing some very cool, very low latency augmented reality displays. Peter?
Thank you. Thanks for the introduction. And so now I'd like to talk to you about developing low latency displays for augmented reality. And over the course of this talk, I'd like you all to learn about some of the problems faced by AR displays and how to go about solving them. More specifically, by the end of this talk, you should have an idea of how we turn the results on the left into those on the right. These two checkerboards you see moving back and forth, physical and virtual, became aligned as the display turns. And in addition, how we transform display with inconsistent brightness into one that adapts to changing lighting conditions in the physical scene, adjusting the brightness of the virtual objects in that scene. But what do I mean by virtual? Some of this may be a little bit low-level background, but just to give a framework. I'm sure you're all familiar with VR displays. They present a purely synthetic environment created in the computer, and more often now than ever before, VR experiences have taken the form of games, a few of which are pictured here. And this recent increase has resulted from the recent release of a few consumer-grade VR headsets, which have brought VR out of the lab or museum and into the home. However, a common element of VR displays is a total blockage of the real world. The head-mounted display covers the user's field of view, disconnecting him or her from reality. Other types of displays, on the other hand, allow for the mixing of the real and the virtual. And these types of displays comprise AR, or augmented reality. They keep most of the real environment visible, adding little components here and there. As a result, the user is able to maintain a real-world context in the mixed reality environment. AR displays are also a lot more diverse. Of all these types of displays, you might be more familiar with optical see-through, given the HoloLens, but video see-through has been popularized by things like Pokemon Go, which has downloaded 500 million times on people's smartphones. Spatial or projective AR, like the one on the left, uses digital projectors to illuminate an otherwise blank white object into a different, more colorful synthetic appearance. But optical see-through is going to be the focus of my work presented here. Optical see-through doesn't block the real world in any way. The real and virtual are optically combined with translucent displays, mirrors, and/or lenses. Several commercial products exist in this area. I'm sure you're all familiar with the one on the left. But some other ones can be either self-contained or require tethering to a PC. Now, there's two main challenges in optical see-through AR that I focused on in my research. The first is registration error, where the physical and virtual worlds become separated or misaligned. And when a user experiences this problem, it can be distracting or cause nausea, neither of which is very good. A second issue is appearance inconsistency. And this is where the physical and virtual objects don't appear to exist in the same world. In this example, the rightmost teapot is way too bright for its background. And this can be distracting or blinding if the virtual object is too dark. Then it can be indiscernible. Now, the combination of these issues breaks presence, or the user's sense that they are in the mixed environment. And we want people to feel like they're in that mixed environment. So the question is, how do we alleviate these problems? Now, the thesis statement for my PhD was twofold. In augmented reality displays, the combination of performing post-rendering warps in display hardware to mitigate latency registration error and using scene-adaptive high dynamic range color to improve the consistency of virtual and real imagery decreases the disagreement of the two worlds. Now, in order to demonstrate my thesis, I wanted to do the following. First, I wanted to resolve registration error. And for that, I needed a low latency, high frequency display, and I performed post-rendering warp in the display. Second, to maintain appearance consistency, I needed an HDR color display system. And so I did. I created a low latency, optical see-through, augmented reality, color, high dynamic range, head-mounted display. And this particular display had an average motion-to-photon latency, that's when the user turns and the display updates, for a grayscale of 80 microseconds, yes, microseconds, and for 16-bit RGB HDR, 126 microseconds on average. For comparison, a normal conventional display would be on the order of 10 milliseconds or 10,000 microseconds. So in order to discuss this implementation and the design principles behind it, I'm going to cover the following topics. Mitigating registration error, generating the appearance, maintaining the appearance consistency, and then conclude with some summary. So let's begin with mitigating registration error. A little more outlining here. So start with some causes and effects of registration error, some prior work that others have done in trying to mitigate it. Talk about the render cascade pipeline, implementation details, and some visual results and some latency results. Let's first take a look at registration error. Now, there's a lot of sources of registration error in systems. Static error, which tends to be related to calibration or physical properties of the system. Dynamic error, perhaps the quality of the tracking system. But the greatest source of error, outweighing all others combined, is latency. And that's the tracking system latency, the rendering system latency, the system overall latency in getting the images out onto the display. But latency overall is the greatest source of error. Now, how do users perceive this sort of error? Basically, virtual objects seem to move discontinuously from when the user moves. So let's take a look at an example, or a pair of examples, rather. Suppose that we have a blue ball that we're going to add an orange outline to. And now suppose that the user is looking at this ball and turning their head such that it seems that the ball is moving to the left. Now, in the best case, the real and virtual object would seem to move together. However, there's a couple of issues in reality that makes it not so simple. The first sort of way that this error can appear is swimming. And that's where the virtual object seems to lag the real object. So here's our physical and virtual objects again. We're going to take a look at it and how it moves over time. And so as that ball moves to the left, the virtual outline around it is delayed behind it. And a judder is sort of a different effect. That's where the virtual object seems to smear or strobe. And so let's take a look at an example of that. And so now as the jumped ahead. So now as the ball is moving, that virtual appearance seems to catch up to it in stutter steps. And it doesn't take very much latency to cause these effects. Say in just 10 milliseconds of lag, looking at an object 2 meters away while turning 150 degrees per second, which is not very fast for a head turn speed, that will result in 5 centimeters of error, which I'd say is quite visible to the user. So how much latency is too much, though? Now, for VR, Oculus has recommended less than 20 milliseconds. But for optical see-through AR, the tolerances are a lot smaller because the user can still see the real world behind the virtual. And so pose differences are very noticeable. Now, there was an article that discussed for aviation purposes that the latency needed to result in no more than 5 milliradians of discrepancy. Now, for a very slow head turn speed, okay, that's a pretty good latency tolerance. But as the user starts turning their head faster and faster, and 437 degrees per second is sort of a speed that someone would turn and look if they know where they're turning to look at. That's a very small latency tolerance. So how have people in the past gone about trying to resolve these issues? I'm going to talk about 3 main methods. The first is frameless rendering. And the key detail in this is that while normal rendering is a series of complete frames, in frameless rendering, you're doing fast incremental updates to the scene. It's less like a movie and more like a bunch of small tweaks to the image. And in those tweaks, the aggregation as perceived by the user yields a perceived image that should be better. Another idea is post-rendering warp. And the idea in this one is after someone performs a normal, slow rendering operation, expensive 3D rendering operation, they follow it up with a much faster warping operation that makes a correction of the perspective. The key idea is that while the slow rendering operation used old pose data, the correction, which can operate quickly, can just grab the latest tracking information and hopefully produce a nicer scene. And as far as I know, the Oculus, the Vive, and NVIDIA graphics drivers all support in the driver post-rendering warps for VR purposes. And these post-rendering warps are made possible because of recent GPU improvements, more specifically GPU preemption. As a result, they're able to delay that post-rendering warp operation as late as possible in the GPU, minimizing the latency between the measurement and the transmission to the display. But this is still happening in the PC, and we can benefit by making this correction even later. So, to combine each of these ideas, conventional rendering is expensive, and it delays the output. And if we perform incremental updates, we can reduce the complexity and be able to update faster and more frequently. And lastly, displaying that post-rendering warp operation as late as possible reduces errors due to latency. So, from all this, I present the low latency render cascade pipeline. In this, we start with, say, conventional rendering on the PC and followed up with a series of post-rendering warp operations from before. But after that, we can do even more warps, each of which is operating faster and faster than the one before. Some sort of warps like 2D warps or skew, rotation, offset translation, those can happen later because they can operate very quickly. At the very end, we'd like to perform radial distortion correction to correct for any optical issues in the display. Now, this is sort of a complicated allocation of it. In order to actually test this idea, I take this notional pipeline and simplified it into a subset of all these warps. Simplification is that in order to examine post-rendering warp in the context of display hardware, and partly due to the low latency tracking systems that we had available. So more specifically, we're going to do normal rendering in the PC, do radial distortion correction on the PC, but then perform a 2D offset correction in the display hardware itself. So let's take a look at some of the hardware used to implement our prototype system. The first was the tracking system. For low latency, we used a pair of shaft encoders. So we could measure the user's pitch and the user's yaw. And these particular shaft encoders gave us a latency of about 30 microseconds at most. The system was intended for use by a person, but for all the videos that will follow, we put a camera where the user's eye would be. All the post-rendering transforms I described are operating in an FPGA that's attached to the display. And more specifically, the operation we perform is a 2D image translation. And lastly, the display itself. For the high-frequency, low-latency display, we used a DMD projector, which was capable of a binary frame rate of 16 kilohertz. But what exactly is a DMD? A DMD is a MEMS device, a microelectromechanical systems device. And it's basically a grid of mirrors, each of which represents a pixel, on a chip. And each of those mirrors can be tilted electromechanically to two different positions. Either, say, to on, where the light bounces off the mirror and out the lens, or off, where the light bounces into an absorber or back towards the lamp itself. Now, typically, in these systems, the light source is constantly on. So in order to get gray levels out of the device, one must flip these mirrors back and forth very quickly. In order to get color out of the device, one often divides either with time by using a color wheel or multiple colored lamps, like LEDs, or with multiple DMD chips, each one with a separate lamp. But how do we go about controlling a DMD device? Well, a DMD is basically a double buffered device, where you load the back buffer with a series of binary pixels, and then at some point commit all those pixels to the mirrors, and they all flip together. But there's some constraints with this sort of operation because it's a physical system. Those mirrors require a little bit of time to move and stabilize, and the mirrors update in regions of the display. So as a result, the optimal loading strategy for updating this display is basically raster order, top to bottom, back buffer loading, and interleave the commits of those mirrors to the display. Now, all of this brings us to the overall data flow in the system. So there's some items to note in here. Specifically, that the tracking data from our tracking system is supplied in excess of both the PC and the display's frame rates. The PC is supplying an image that is a lot larger than the output image of the display. And the display's FPGA system is transforming the image and feeding binary pixels to the DMD. Let's take a look at how that transformation works and why we need the PC to render a larger field of view. So this is how we're generating the images. Suppose first that there was no difference between the live tracking pose and the GPU rendered the image tracking pose. Now in this case, we're going to just take the center of the image, and that data is going to get passed on to the modulator. They're split up into multiple regions to illustrate that incremental update of the DMD. On the other hand, if the poses were different, namely because the user's moved, and the user's going to often be moving, since the PC rendered that image, we're going to pick a different region and send that image onto the modulator. Essentially, it's very straightforward. We're using the difference in the pose angles for that tracking system, it's 2DOF, and multiply it by a calibration ratio that's dependent on the display's resolution, field of view, and so forth to get the offset from the center of pixels. Now, the field of view requirements needed to actually over-render the image is dependent on the frame rate of the PC, the latency in the system, the field of view of the display, the output resolution of the system, and the maximum head turn speed that we're expecting the user to move with. So in this case, we were rendering 1080p video at 60 hertz, which gave us the ability for the user to turn their head left and right at 440 degrees per second, which is not a bad speed, and vertically at 150 degrees per second. So what does all this look like in practice? So for this first system I'm going to present, it's a 6-bit per pixel grayscale system, which is the first one we got working. The physical scene consists of a small checkerboard that's located about 2 meters away from the display, and the virtual image is the corresponding checkerboard. So if no errors in the system, those 2 checkerboards should be exactly aligned. But let's first take a look at what an uncompensated system looks like with conventional latency effects. So in this example, we're moving the viewpoint back and forth at about 50 degrees per second. And this bottom portion of the video is recorded with the camera looking through the optical see-through display. And the other 2 are just some observational cameras. So let's play that again. Come on, let's play it again. So in this video, take a note at the bottom that virtual overlay is lagging significantly behind the physical counterpart. Now here's the result using our algorithm, running at the same back and forth speed of 50 degrees per second. And notice how those physical and virtual overlays stay much better aligned than they did before.
Peter?
Mm-hmm. Yes?
Do you make any effort to predict
Nope.
what's going to happen?
Nope. It's all live data, so there's no prediction in the system. And here's the same 2 played back at 1/8 speed. So in this video, the top one is the uncompensated system, and the bottom one is our algorithm. And so take a note in the difference in divergence while the HMD is slewing, and the similarity in convergence while the HMD is idle. Also note that in the conventional display that the overlay shows both swimming and judder effects, whereas in our display the overlay seems to move smoothly and consistently.
But you could try to predict and stick the virtual out there at the predicted place where the camera's going to be, right? That should possibly help things.
So in my experience when I was trying to do prediction stuff before, it always ended up looking worse than not actually predicting.
Because you don't know where you're going to stop,
Right.
accelerate, and then go back.
If someone is moving at consistent speed, then you can jump ahead very quickly, but it's when someone is changing their acceleration a lot that you tend to overshoot or undershoot. Undershoot when they're starting and overshoot as they're stopping. And so this particular system doesn't use any prediction in either system. There is actually some possibility for prediction on a different timescale that might be helpful, in that if you predict where it's going to be, you might be able to make a smaller compensation operation in the display. Unless you still run into the same issues where overshooting, undershooting, and then you end up picking different regions anyways. But
in the top image, what was the motion-to-photon latency?
50 milliseconds.
50.
And the bottom one was around 80 microseconds. Another question?
Can you talk a little bit about why, even in your algorithm, when you switch directions, you see some swimming?
Yes, I can actually.
Can you go back? I didn't notice that.
Okay, sure.
Yeah, it's a little bit of it.
It's very noticeable.
There's also camera effects
when he switches directions.
It's a
So this is
smart.
filmed with a GoPro running at 240 hertz, by the way.
See the swimming right now?
Yeah, I see it.
Now it's
So I
It's
think,
a lot
can I pause it?
less, yeah.
Yeah.
now it's
So you're talking about this
Yes.
right there?
yeah.
So in this particular system, we used all aluminum pieces for mounting everything. And as a result, the display was moving along axes that weren't being tracked because the aluminum was deforming that it was mounted on. And so we later replaced that with steel to fix that particular issue. So if we had actually stopped moving in either in these particular cases, both images would diverge in a similar amount. So this particular offset that you're seeing is actually because of the camera, the viewpoint pose is not where the tracking system thinks it is, even live. And so it's because of the deformation that the viewpoint hasn't
It
aligned.
looks good on the right, but not on the left.
Yeah.
That's what you'd expect.
And similarly, when the image is also disappearing on the right, that's because we're leaving the field of view of the display. It's only 33 degrees along the horizontal.
So when you went to steal and fix this issue?
It fixed that issue. When it's a lot more rigid and we're actually tracking correctly where the display is moving, then that fixed that issue. Any other questions at this point? Yes.
You said the registration model was 2D translation.
Yes.
That's just one 2D translation for the whole virtual image.
Yes.
Not any per pixel 2D. It's not like a flow.
Every pixel moves in the same amount.
Same amount.
Yep.
Now,
The idea was we want to, in order to be able to run the system very fast, we wanted a one-to-one mapping of pixels.
right. But in realistic systems, that model is too simple, right?
Yes.
So can you comment a little bit on if you wanted a more complex warping model?
Sure.
What would it take?
So the idea along that is more along the lines of that notional pipeline I showed earlier, in that while this operation could be the very last operation you performed, you probably want something that's more depth dependent, or even, this also doesn't support this axis either, of rolling your head, that you would want other operations to occur. Now, those operations may be more expensive computationally, and so they can't operate as often. In this system, we were performing this operation on every binary frame that went to the DMD, so at 16 kilohertz. So if we were trying to do a depth-dependent warp that required more complicated math on a per-pixel basis, we would drop the frame rate on those operations. But the advantage is that it brings it closer into alignment, so that in theory, the 2D correction at the very end, compensation, correction is a little bit of a strong word, compensation, would have a smaller operation to make. And the whole idea of these post-rendering warp ideas is that as long as the operation that you're making is a small enough change, then it should be better than not making the change. So, yeah. And we only explored this 2D operation because the tracking system only supported 2D operations. And we wanted to be able to look with a sort of a gold standard tracking system, as opposed to one that adds a lot of latency into the system. Any other questions at this point? Okay. So here's that image again on still. Of course, for this one, I picked one of the better looking ones, but you guys caught the right issues, and I had an explanation for it. All right. So how fast is our system? And I seem to have lost focus. Come on. There we go. So a typical way of measuring motion-to-photon latency is by using some repeating event that can be accurately measured at multiple points in the pipeline. And for this system, we used an oscilloscope and measured the time between crossing 0 degrees on the tracking system and a change in the output. Now, in order to see a change in the output, we modified the system so that it would draw black if we were negative and white if we were positive. I know this is the actual measured angle, not a difference in angles between live and render time. But all other components of the system remain the same. Now, in order to classify the measurement, we separated out several components of latency and captured 4 different events. The initial time when the 0 crossing occurred, this is the initiation of the motion. The time when the display system received confirmation that the 0 crossing occurred. The time when the display system commanded the DMD in order to change the output intensity. And lastly, the time when the DMD actually changed the emitted light in response to that command. Now, in the example on the left, which was a single sample, each of these events is represented by a raise in the waveform. And in this particular one, the end-to-end latency was 97 microseconds. Now, in order to examine sort of the range of possible latencies, we used a different mode of the oscilloscope, where the bands of vertical rises, like, for example, this, represents the minimum maximum possible situations. And our particular system actually has a uniform distribution of latencies. So the average is actually in the middle. So, and the average latency for this particular implementation was 80 microseconds. Now, a reminder for compensate, the uncompensated system was 50 milliseconds, or 50,000 microseconds. Our system, on the other hand, nearly 80 microseconds. Now, it's worth noting a few things. First, a significant portion of the end-to-end latency was still due to the tracking system we were using, which ranged between 15 and 30 microseconds of lag. And the variation in the latency was mostly due to the phasing between when the motion was detected and transmitted and when the frame was going to be transmitted. And it operated best when the motion occurred just before we were about to send a frame to the DMD. And it operated worst when the motion event was received just after we started transmitting. We didn't change the image partway through an image, so every binary frame was a single pose piece of information. We didn't want to deal with any image tearing artifacts. So, returning back to that system data flow diagram, the next problem is how do we take these PC-generated input images and generate a series of binary frames on the DMD? And that brings us to generating an appearance. Now, this generating the appearance on these binary displays is a task for modulation. I'm going to discuss some classic modulation schemes first before talking about my new algorithms and its results. But why do we care about modulation at all? Well, recall that a DMD is a binary device. Each pixel can only be on or off. And so in order to generate that grayscale, we need to flip that mirror back and forth at a high frequency. Now, there's a bunch of prior strategies for modulating these. A very simple one is pulse width modulation, or PWM. Now, in these graphs at the bottom, the orange color represents the on times, and the black represents the off times. And so I'm showing 3 cycles of 4-bit pulse width modulation. Now, pulse width modulation works by performing 2-part pulse groups. You got the on pulse for some amount of time and an off pulse for some amount of time. And those on and off times are proportional to the amount of brightness that you want. So it's directly width proportional to the desired intensity. Now, the advantage of pulse width modulation, very simple to implement. Disadvantage of pulse width modulation, produces low frequency harmonics. And more specifically, you can see a visible flicker at particular operational rates. But it also doesn't require any memory issues. Delta sigma modulation, which is a type of pulse density modulation, tries to optimize the pulse sizes. It still has the same numbers of ons and offs as pulse width modulation, but each of those on-off transitions occur more frequently. So if we compare these 2 graphs, you can see the amount of on and off time is the same between them, just we're changing it more frequently. We're maximizing those transitions. Now, there's some issues with this, that it requires a lot of additional memory. You now need to basically keep an accumulation value in order to operate. But it reduces those high-frequency harmonics, so you get rid of that potential flicker issue. So how can we improve upon these? So we want a new algorithm that was compatible with the low-latency rendering operation. It has the memory cost of pulse width modulation, namely no additional memory, but have behavior similar to pulse density modulation, namely high-frequency modulation to keep that flicker away. And so we created pseudo-random pulse density modulation, where essentially we use a looping random number generator. It produces the same numbers of ons and offs as either of those previous 2 methods, but it produces a random permutation of those ons and offs. So we get good numbers of transitions, but it doesn't require any additional memory. So the way this works is we compare a random number with the desired intensity. If it's less than the desired intensity, we choose on. If it's more than the desired intensity, we choose off. Or if it is the desired intensity, we also choose off. Makes it very simple to implement, and it produces high-frequency harmonics, so we avoid that flicker issue. And so with this particular modulation scheme, for 6-bit per pixel grayscale, we got 15,552 hertz binary frame rate. For 6 bits, it only required 63 binary frames per integration cycle. That's the cycle required to produce a grayscale value. And that was, from this particular system, about 4 milliseconds. And so visually, it looks pretty good. So this is a demo of PR-PDM with a grayscale image, a little bit more exciting than that checkerboard. In this video, the HMD is still slewing back and forth at 50 degrees per second, but the photo object is registered to that checkerboard, so you can still see the tracking. Note that the portion of the overlay that's intended to be aligned continues to remain aligned despite this fast motion. Now, while we have now a low latency display, and we're looking at algorithms for low latency operation, we still want them to look appropriate for the real world. We want them to be a little bit more exciting. And so that brings us to one of the last major topics, and that's maintaining appearance consistency. And the motivation is high dynamic range. So I'm going to talk a little bit about what it is, some prior work in high dynamic range, another new algorithm for modulation, and scene adaptive brightness. So why do we care about color and HDR? Well, we want to match the real world. The image on the left isn't quite going to cut it. It's kind of a dull grayscale. And the image on the right isn't quite right either, because that rightmost teapot is way too bright for its dark background. It would kind of blind the user as they're looking at the display. But the real world is also a high dynamic range environment with great variation in scene brightness. And that variation can vary both spatially, both typically in the form of shadows, temporally with the time of day, or extremely with unique environments, or perhaps maybe the eclipse coming up. Now, for compelling augmented reality, the virtual image must match the real world. Otherwise, the virtual is invisible, blinding, or simply disconcerting. Even this simple meeting room pictured here has vastly different brightnesses across the scene, across multiple orders of magnitude. But how have people created HDR displays in the past? Typically by combining spatial light modulators. The example on the left uses a low-resolution LED backlight with a high-resolution LCD panel. It's actually similar to, I think, how current TVs work. And basically, they split a 16-bit HDR response between that LED grid and the high-resolution LCD. The system on the right combined a high-resolution projector and a high-resolution LCD panel. In this particular example, they specifically misaligned the two so that you can see where those are each contributing. And they were able to get a contrast ratio of about 700 to 1 with their system. Now, all the previous modulation schemes I talked about, pulse width modulation, pulse density modulation, the pseudo-random pulse density modulation, they all require exponential time in order to modulate. Now, that becomes a bit of an issue when you want to start doing HDR, say 16-bit RGB HDR. Well, then almost 200,000 binary frames would be needed to show all the possible variations you could get. And an integration time of 12 seconds is not very good for an AR display. So what can we do to alleviate this problem? Well, we need another new algorithm for controlling the display. We want it to be still compatible with low latency rendering. We want it to still have the 0 additional memory cost. And we need it to be faster than exponential time with regards to the bit depth. So introduce direct digital synthesis, DDS, which combines the binary modulation of a DMD with a fast variable brightness illuminator. And with this system, we were able to get an integration interval that was linear with regards to the bit depth. So let's take a look at what the algorithm looks like. Let's take a look at a small example. Basically, you start with a most significant bit, and for every binary frame, for every pixel, we examine the bit value for that. Say that starting with the most significant bit. If it's on, if it's a 1, then we turn the mirror to an on position. If it's off, then we turn it to the off position. Set the illuminator that we're going to shine on this DMD to the appropriate power of 2 brightness. For that MSB, we want maximum brightness, then half, then quarter, and so on and so forth. And then advance the bit index and cycle. So let's say we're trying to produce the intensity 10 as a 4-bit number, which could have ranged between 0 and 15. Well, in binary, 1, 0, 1, 0. And so we need to flip the mirrors, control the brightness illuminator, and that affects what the eye is going to see. And so basically, we cycle. So the illuminator is going to do the powers of 2 intensity. We're going to cycle on, off based on that binary value. And so the user is going to see a combined brightness that is about, 5/8, or which is about 10/15. So let's compare all these modulation schemes and kind of what they look like. In each of these graphs, we're seeing 4 cycles of 4-bit pulse width modulation, delta sigma, and PR-PDM. But in that same amount of time, for we're able to actually perform 16 cycles, or rather 15 cycles, of direct digital synthesis. And so note that these heights of all these graphs have been normalized so that all 4 algorithms are outputting the same actual energy intensity. And while these schemes all use a constant illuminator, this one uses a variable brightness illuminator. The basic idea is direct digital synthesis is linear time as opposed to exponential time. Now, because we're starting to mess with the illuminator, implementing direct digital synthesis required a few hardware changes. We needed that high-frequency controllable light source. So very fast, pulse of light, variable brightness, and synchronized to the DMD. We were able to get some good results with it. More specifically, for 16-bit RGB, we were able to achieve a fifth. Oh, sure.
How the hell do you do that?
Okay.
Is this commercial stuff? Is this stuff that you totally designed yourself?
So my focus was on programming the display to take advantage of it. And my fellow grad student, Alex Blate, designed the hardware that actually drives the LCD. And that's going to be part of his dissertation. But more some basic ideas on it. We're not using pulse width modulation to control the light source. That's normally how you control an LED to change it on and off very bright, or very, very fast. But we'd need a 5 or 6 gigahertz modulator, and most LEDs don't like changing that fast. So it's a series of very precise op amps combined with a DAC that basically drives the voltage we want exactly, the current we want exactly. In order to be able to turn the LED on and off very quickly, we keep it in a nearly on state so that we aren't going to get the initial overshoot that you get when turning on an LED, or the delay before shutting off, because we're going to, when we want to turn it off, we take it to that nearly on state again. And so the LEDs are brightness controlled via the current, and so we're able to basically produce the exact brightness that we want after a color calibration step.
So why do people typically just turn the LEDs on and off versus doing this thing? Does it take more power? What's the?
If you were only trying to do an 8-bit display, then you can control the. You can either time division multiplex it, so you're spending, say, half the time on that most significant bit, then a quarter of the time on the next most significant bit, and so forth, and just keep the LED at a particular brightness. And with a 16 or 32 kilohertz display, I think you can get about 7 bits out of that. You could just have half the time be at full brightness and half the time be at a different brightness, and so that way you don't have to pulse the LED very quickly. You can just, again, with time division multiplexing of it. That's mainly how most of those DMD projectors work.
There's got to be some limits on the, like if you keep increasing the power of the light source, at some point you're not going to be able to modulate it effectively, right?
We were able to make it uncomfortably bright, at least within a lab environment.
The sun is pretty uncomfortably bright.
Yep. If I recall correctly, we're not quite bright enough to overwhelm the sun.
That's not what I mean, though. I mean, can the mirrors still get you fine detail around that stuff, or this?
Are you talking about that the light is spilling off of the other mirrors? No, that really wasn't an issue, actually. The bigger issue with regards to the getting diffusion of the image was when we were using a back projection surface for the projection. We ended up eventually doing direct view so that you're looking essentially through just lenses at the DMD itself. Originally, the back projected version was a little bit blurrier, but we didn't have any blurriness issues resulting from a very bright light source, because when the mirror is in the off position, it's reflecting that light into, actually back at the lamp itself. So it's not leaving through the lens system.
The mirror is, but there's stuff around the edges of the mirror and all that too. I don't know if that. Don't worry about it.
I didn't notice any issues.
It works. It's
So. But with this, we were actually able to get 16-bit per color in 48 binary frames as opposed to 6-bit grayscale in 63. So the integration cycle is actually shorter on this system. So it's faster than PR-PDM at greater color depth. So for this particular example, the desk that we're going to show some virtual objects on is about 3 meters away. We've got a series of light sources around the room, including a very bright LED.
16-bit per channel.
Per channel.
So 48 bits.
Yes.
Okay.
Yep.
That's great.
And then that's for the lamp that you're going to see in the room, that's a 250 watt equivalent LED light that was driven by a DC power source, so it actually was even higher watt equivalency. Now, in the first demo, the input to the system was a pair of colorful static teapots of identical appearance. And this is just to show the maximum range of the system. So the viewpoint is static, and the system is configured such that the left teapot is using the upper 8 bits, and the lower teapot is using the lower 8 bits. Now, the range is exceeding that of a normal camera. This is a standard dynamic range camera, or a low dynamic range camera. And so in order to be able to film it, we use a neutral density filter that we move back and forth in front of the lens, so that you're able to see both teapots. But the one on the left is 256 times brighter. The particular filter that we were using was cutting 98% of the light. And so here's some photos again of the same experiment. So you're able to see the lower 8 bits, the upper 8 bits, and both together with the neutral density filter. Now, the next demo that I'm going to show, in order to verify that we still have a low latency capable display, uses a different input. The teapots are now 3D rendered, spinning, textured, colored, and they're spinning around their own axis. And the display's pose is unlocked so that the display is able to move. Now, in this demo, the teapots have fixed brightness, and we're moving the display at different speeds. Starting slow. So latency compensation disabled is on top, latency compensation enabled is on the bottom. And so you can see a little bit of judder on the top one, and that they're starting to shake on the table. But very stable on the bottom one. And I remind you that 50 degrees per second is not a very fast head turn speed. That's about like this. So the misalignment distance increases with that rotational speed, and it's just like those checkerboards that we saw earlier. Now, the latency analysis for the system is very similar to that of the previous implementation. The latency variation varies mostly as a result of waiting for the transmission and stabilization of the mirrors to occur. In contrast, the PR-PDM system had a constant on illuminator. So as soon as the mirror moved, you could see the change. Now we have to wait for all the mirrors to move to the right position before we pulse the light for a very short time. And so these changes take more time. So overall, this HDR system had an average motion-to-photon latency of about 126 microseconds. This isn't quite everything yet. Now that we have HDR support, how can we make sure that the virtual and real objects seem to better coexist? Well, adaptation. One more modification to the system. We used HDR light sensors to observe the real environment. These are shown up here at the top right. We're using just a horizontal array of 4 sensors. Each sensor is observing a separate horizontal quarter of the display's field of view. These particular sensors, though, they only operated at 40 hertz, but we interpolate their data at 1514 hertz. That was limited by how fast the CPU could run controlling them. And in order to interpolate them, we use 5 piecewise linear equations spatially and an error decay function temporally. Oh, excuse me. Now, this conversion operation is occurring in the display on every binary frame. We take the GPU's 8-bit per color output, so standard or limited dynamic range. The display is going to interpolate it based on the measured scale factor. That's basically a comparison of the measured scene brightness in that region compared with the maximum supported brightness. So if it was as bright as was fully supported, we're going to basically shift all those 8 bits into the upper 8. Say if it was half as bright, half, shift it up only 7, and any fraction there in between. So the HDR modulation output is a product of the GPU pixel and that scale factor. And to demonstrate this, I have a pair of demos to show. They use the same spinning teapots as before. In the first of these demos, we move a pair of narrow beam flashlights of differing brightness around the otherwise dark physical scene. Note how each teapot brightens and darkens relative to its proximity to the spotlights. The brightnesses of the teapots also remains aligned to the teapots as the display rotates.
You know, GPUs have 10 bits out nowadays, right?
Yeah, but we didn't. We want to put the adaptation as low latency as well, so that's why it's on the display as well. We did talk about running the GPUs in a high dynamic range mode, and it would require a little bit of a change to the memory architecture we had in the system, because now the system would need to store all 16 bits as opposed to computing it on demand. But there are some other reasons you'd want HDR instead. The focus on this was just the last scene adaptive step. And one more demo of scene adaptive brightness. So it's the same teapots, but I'm going to be moving a very bright desk lamp back and forth. And again, note the matched response of the teapots to the light.
What was the resolution on your light sensor?
There were 4 in the brightness resolution, or the
lateral resolution.
There were 4 sensors. Each is a 1 value sensor. They each give an ambient light value as measured. The reason we were able
So 4 just laterally.
4 lateral horizontal sensors, and that was partly because we hadn't found an HDR camera that we would like to be able to put in that particular spot for it to get a more per pixel basis. So instead we were just interpolating it. And each light sensor is basically physically limited as to what it can see with the baffle. So we're nearing the end. Let's return to that original 2-part thesis statement. Augmented reality displays a combination of performing post-rendering warps in display hardware to mitigate the latency registration error and using scene adaptive high dynamic range color to improve the consistency of virtual and real imagery decreases the disagreement of the 2 worlds. The main idea was that of performing incremental operations. First, by incrementally re-rendering the scene in the display hardware, and second, incremental aggregation of the appearance over multiple steps or binary frames. Now, again, generating that multipass aggregate required modulation. The classic algorithms were simple, but they can cause flicker or they cost memory. PR-PDM reduces that flicker and memory cost, but while it was good enough for an 80 microsecond grayscale display, it wasn't good enough for color or HDR. And direct digital synthesis also reduced that flicker and the memory cost and was able to achieve much greater color depth while still having low latency capabilities with 126 microseconds for a color HDR display. And with DDS and some HDR light sensors, we could scale the brightness of the virtual scene by matching it to the physical scene. But what are some other limitations in the current system, and where can we go from here? Well, there's several. Let me talk about some of them. First off, with regards to inertia, the system's way too heavy. It's more a display that wears you instead of you wearing it. Instead, if we weren't using these standardized boards and using more specialized task optimized hardware, we could probably shrink this down a bit. And currently, the system uses shaft encoders for low latency, but they limited the motion to yaw and pitch. At the time, no known commercial tracking system provides the 60 equivalent at the latencies that we were targeting. Specifically, the latencies we were targeting. There are accurate systems out there, and they'll give you 6 off, but not at 30 microseconds.
What was the fastest you did find?
We tried the highball tracking system, and that was best case 16 milliseconds. And the OptiTrack didn't test latency, but it's only a 100 hertz tracking system. The OptoTrack tracking system, no latency characterization, but it the way it operates is a given LEDs fire at 2600 hertz, and then you divide that by the number of LEDs you're using to track with, as well as dividing by, I think, 1.6 or 1.3. And so
So there were no mechanical 6D things, because I think there used to be one, right?
we had a ferro arm, which could,
Yeah, booms, that's what I was thinking.
that would but it only operated at 25 hertz.
Oh, wow. Okay.
So,
For some reason, I thought they were fast.
well, there might be faster ones now, but for the equipment that we had, this was
Okay.
the best we could do.
Okay.
Do you have any ideas about how you might make a system that had a tracking system that had lower latency? Like a super version of the eyeball?
I'd be willing to talk with you that offline, but not on a setting that's going to go on public video. Sorry.
But actually, with respect to that point, these systems could do, there could be like a predictive, like a dynamical system which could run at a much higher frame rate. It would not be, it would be doing, like, we talked about prediction earlier, right? That sort of a software could be combined to work at higher frame rate. So I guess you're not talking of those solutions. Like,
So if you had a tracking system that operated at least faster than the display rate, than a conventional PC display rate, my issue with prediction is sort of the how long are you going to try and predict in the future. The smaller you can make that window, the less error you're going to result from your prediction. That might be not quite the answer you're looking for, but
I was just thinking of like when people are doing visual inertial SLAM and saying that their systems can run at really high frame rate. What they're basically saying is that the visual subsystem runs at 30 hertz or so.
oh, you're talking about sensor fusion, or
Yeah.
like those sorts, where you have a visual system that's running at camera rates, and the inertial system it runs at a kilohertz.
Right.
Yeah. Okay. Yeah. That has some possibilities, but I hesitate to say more right now. I'm sorry.
Thanks.
So then, some more future work potential. Algorithmically, the current system was only exploring this 2D offset, and again, limit because of the way that we were tracking. And that radial distortion correction was operating the GPU, which actually meant that the 2D translation occurring after the GPU could shift it worse than if we hadn't performed the radial distortion correction at all. Because it might have wanted to shift one pixel 6 pixels one way and another pixel next to it 7 pixels the other way. When you do global 2D offset, that can cause some issues. We'd like to put radial distortion correction at the end, or even more stages, so that if we had a better 6-DoF tracker, we could explore doing more of these warps in between. And it's possible that the selection of these warps might be situationally dependent as to what the use case is. That's sort of another open question as to what could be seen. Now,
What do you mean by that?
if the user is likely to be moving translationally, and the objects that they're looking at vary greatly in depth, then you are more likely to want a depth-based correction. But if you're only generally looking at an overlay that is at one depth, then you might not need that depth correction as much, or you might be able to do a single depth dependent correction that operates globally as opposed to per pixel basis. Now, part of the reason this 2D offset operated very fast was because it was highly parallelizable for the one-to-one relationship. And some of these other corrections might begin to require some crafty memory algorithms there. 16 bits of high dynamic range is nice, but for that photograph I showed in the meeting room, it's not quite enough. The current system used fixed width pulses to illuminate the DMD, and 10 microseconds was the longest pulse we could put it in there before it would start interfering with the mirrors changing on the next frame. But by adding additional shorter pulses of light, we could, even with those 16-bit DACs, there's a 16-bit part there, we could get even deeper darks out of it and widen the dynamic range, possibly as good as 20 bits per color based on the minimum time we could pulse the light on and off. It was about 600 nanoseconds of rise and fall time on that light, by the way. And then scene brightness detection. As you commented earlier, very low resolution spatially that we're looking at this, which produced occasional artifacts on those transition zones because we were doing a linear interpolation between them. So alternatives would be some higher spatial resolution, sensor arrays, HDR cameras, a second DMD as a camera, where you're doing some crafty math with a single light sensor where the LED would be for a DMD. And so last, scene relighting. As opposed to just trying to scale the brightness so that we're not either blinding the user or hiding the image completely, a system could take a look at what the scene room conditions are to figure out where the lights are and adapt and relight the scene, which gets into some computer vision research. So, to conclude, present some work on that focus on algorithms for optical see-through AR-based systems that use, say, DMDs or other spatial light modulators that are fast. And VR systems could also benefit from low latency HDR displays despite the less stringent requirements. So I'd like to acknowledge some funding sources that I was funded by for my PhD. More specifically for the low latency displays work was NSF and Being There Center or Being Together Center funded. I was advised by Henry Fuchs and Greg Welch, as well as for the rest of my committee was Oliver Bimber, Anselm Lastra, Montek Singh, Bruce Thomas, and Turner Whitted. There were 2 first author papers by me for this particular work, and several other papers I did while at UNC. And so I'd like to thank all these people that worked with for all my time at UNC on various parts of the projects. So thank you, and thank you for your attention.
So if you were going to build a VR type display, would you still use these digital mirror devices?
So
see-through?
the issue with these DMDs is sort of the bulkiness, because you got the DMD, you got some sort of lens system on it and so forth. Now, there are OLED displays that can be operated in a binary fashion at 1 kilohertz. There was I think a patent or publication by NVIDIA where they were controlling 6 lines of a OLED display at 1 kilohertz. And they could shake this device back and forth and the image stayed locked on. So DMDs are nice for being able to program nicely and sort of set up these optical systems, but they are kind of bulky. So.
Well, it's nice for HDR too, right? OLED would be.
Yeah, because for that OLED, you're running in a binary mode, and so you'd start to run into that integration time issue as well.
Yeah, but the new display actually we're controlling the brightness of
That illumination. Yeah, but other HDR displays used a backlight and an LCD panel, and they modulated both independently to get their 16 bits because they had the 8 bits of the backlight and the 8 bits of the modulator in front.
Can you do something with an LCOS type display? Would that be feasible in a...
So I haven't worked with those types of displays, so I'm not really familiar with them.
Okay.
Have you found any other prior art relating to your changing illumination
So
for high dynamic range?
I think they have been used for like control mechanisms. So I don't think we invented the DDS label for it, but I have not seen it used at these rates before.
So for the second part of the talk, you focused on HDR displays, and you're trying to address this problem of brightness constancy in the virtual objects you're rendering. They seem orthogonal problems to me, meaning that if you didn't have an HDR display, you would still have to solve this problem somehow. Am I right? Understand that?
Which, if we didn't have an HDR display, which the brightness constancy
You
is here?
you still want to solve this problem in the 8-bit regime that you have, and you could still try to solve that problem to a certain extent.
Yeah, I mean,
That's not something you try to do.
you can.
What I mean is this modulation of the colors that you're rendering, and adapting them to the scene brightness based on some light sensing. That could still be done in an HDR-less environment.
Yeah, like think of your cell phones, for instance, where they're adapting to how bright the sun is that's shining on it. Or that's actually sort of the main example I've thought of. You could potentially, instead of having a constant on full intensity backlight, you could have a variable intensity but not pulsing backlight. And so you could cycle either with a normal modulation scheme or still with, well, if you're doing DDS, you might as well get all the bits you can. You can do it faster if you're only doing 8 bits. Or even if you knew that the scene was globally consistently bright and that you were going to pick these particular brightnesses and all the other binary pixels were always 0, skip them. But if you're going to do that dynamically, now you need to rescale your brightnesses so that you're not getting brighter because you're doing the brighter ones more frequently than because you're only doing a subset. So there's a lot of potential adaptations in there.
What's your idea of what you want to do in the next 5 years, research-wise?
So sort of from a general perspective, I'm interested in AR, VR, and something to do with games. And so I like being able to work on projects that involve hardware and software combinations, and that you're able to see something visually at the end of the result, so that instead of just seeing a number on a screen, you can have a system that someone can take a look at and say, oh yeah, I see why that's better than what came before. But that's sort of a general answer. For a more near term, if I was able to keep working on this type of display, I'd be looking into some of these issues I was talking about.
Do you think that this particular design actually has legs in the sense of being able to, really reduce it and turn it into a viable device for commercialization?
I'd need to do some more exploring on sort of what other miniaturization and other sort of display technologies exist as alternatives. So, like, I'm aware of DMDs, but they're a little bulky. I'm aware of OLEDs. They don't operate quite as fast. But I'd like to keep looking to see if there's some alternatives that.
So if you had the path, you would take it.
Yeah.
I see. Okay.
Are DMDs the main limiting factor when it comes to bulk? Are there other factors involved here that we're kind of looking at?
Well, on these FPGA boards, most of the components on those are related to power for those FPGAs. Or they contain components that we weren't even using on the board. For instance, in this particular picture, the only thing we're using on the original FPGA board that controls that DMD, on that FPGA that we can control, is we're just connecting the inputs to the outputs. There's no computational logic on that FPGA. It's all on the Vertex 7, that's the outside board. So if one was able to create a custom board that didn't require a custom interconnect board and a DMD that's only acting as an FPGA that's only acting as wires, and another FPGA that's a black box that TI programmed, if that was all integrated together, and it could be a smaller package.
The electronics, and of course, as John mentioned, the tracking system, right?
Right.
It's something that's at latency levels you want.
Yeah.
Did you take the system and artificially increase latency to see where things got uncomfortable?
So that would be another interesting thing to do from a user perceptual standpoint. We never did any user perception studies because we figured that the inertia in this system would be too much of a confounding factor. But if this is enough, then one could start, yes, injecting delay into the system to figure out what is that threshold, how much is enough, and that might also guide what sort of operations do you need to run at that time scale then. But I don't have any numbers for you on that at this point.
How did you do your, when you say you did 50 degrees per second or 300 degrees per second, whatever, how did you measure that? And
We used a metronome and went
and you had stops for the...
yeah. Well, the stops were as looking at this protractor that
So it's all just kind of
it was approximate.
manual
Human
instrumental.
robot.
It was human controlled. So it was 50 degrees per second on average. So it was probably faster at the fastest and slower at the ends. It was always human controlled, so there was we weren't using a robot to do it that we could then predict. It was still a human in the loop for that. Just a camera was recording it.
You didn't try to have anyone use their neck for that because there'd be no way to put the camera in.
Correct. But if you were to visit UNC, the system is still in place to try out.
Warm up my neck first.
Well, it's all supported by all this aluminum framing. It's a rig that's about this wide.
No way, just inertia. Okay.
Yeah. All this stuff from, if I detach this bar, this is all supported on, I think it was 7 kilograms. It was either 7 pounds or 7 kilograms. I don't remember which
Now,
unit
where
the
did
scale was.
you replace the aluminum with the steel?
On this component right here, that was this shaft. It was basically this shaft could wobble, and that's where all the wobble came from. So the shaft is now a steel shaft with better ball bearings.
UNC grad students now have a fitting on top of that.
And actually, the rig is at a particular height, so that if I am in the chair, I put the chair at the bottom, and if Henry's in the chair is at the height, the maximum height.
So you're the upper and lower bounds.
So we're the upper and lower bounds.
So you actually looked through this thing. And we've seen the videos, which you ran at high speed, so all the artifacts are obvious. What's the perceptual effect?
So you can see the difference. You can definitely see that they diverge and stay stuck together. The bigger issue is that it's a very small eye box. And so the hard part is keeping your eye in the right spot that you can see any image. Now that's mostly a result of switching from a rear projection surface to direct viewing the DMD, which the rear projection surface gave you a larger eye box where you could see the image, but then you could also put your eye more often in the wrong spot. When you're direct viewing, you can only put your eye really in the exact spot, and as long as you can see it, you can see them line up. And without the brightness adaptation, which as you can see why my left eye is so bright here, it's very bright to look at if the adaptation is not turned on, which we can simulate also by just moving a flashlight in front of this light sensors to dazzle people. But I would say one of the more limiting factors is those light sensors with regards to the scene adaptive brightness. But everyone that has looked at it and seen the on and off can see the difference.
Did you or Alex have anything to do with the hardware for the illumination or the display card?
So Alex created the boards, the custom boards for the interconnect, as well as the LED driver board for the illumination.
But in terms of like sourcing the LEDs for the...
We explored several.
And all that stuff.
We explored several, and the main things we were after were that each one had an independently controlled anode and cathode, and that the RG and E were very close together in a common package so that we could put it, they could all fit through the hole that the collimator for the DMD would work.
So you collaborated on that
Yeah.
sort of system design stuff,
Yeah.
the optics and the LED. And
Well, the optics is mostly the stock optics that came with the projector.
you changed the LED. And
We removed the LED package, and Alex developed that part, and then my focus was mostly on the control software on both the FPGA and the PC.
Take our speaker again.